Good morning, everybody. A lot of familiar faces in the room from my previous visit up here with the safety seminar a couple of years back. For those that haven't met me, a little bit about me. I first started flying in 1986. That was with the Air Force Cadets. I joined the Air Force as an engineering officer in January 1989 and graduated from RMIT as an aerospace engineer in December 1990. As is typical of all Air Force engineers, you end up doing a variety of roles throughout your career. I had some weird and wonderful experiences, including being the system engineer for hyperbaric chambers, so some aviation medicine, and aircraft arrestor systems, and a whole lot of other odds and interesting gadgets along the way. I spent the most part of my Air Force career associated with P3 Orions. I arrived at 492 Squadron shortly after, this connects back into Jeff Brown's discussion, shortly after Orion 754 went for an unexpected swim at Cocos. And so the fallout from that fatal accident was very front and foremost at the very beginning of my Air Force career. I left the Air Force in late 1999 and became a civilian contractor embedded still within the Air Force community supporting P3 Orions, and I was doing structural design work. That job had the employer change names a few times, and I ended up running a small design team for Airbus supporting the P3 Orions. And at that stage, late in the career, we had aircraft deployed to the Middle East. And we had a significant event happen in the Middle East which could have resulted in the loss of an Orion over Afghanistan. One of the factors that led to that near miss was that the aircrew were not reporting a particular incident that was in the lead up to this, and it happened several times, these warning events, that something wasn't going right. But because it wasn't having adverse effects on the mission or the flight, it wasn't being reported. So the people who could have done something about the problem had no idea it was occurring. That event resulted in some fairly significant damage to the aircraft and nearly saw me head across to the Middle East to patch it up. But whilst I was putting this together and thinking about Pawnees, I reflected on some of the commonalities between the P3 Orion and the Pawnee. Both have their roots in a very early 1950s design. The P3 was designed from an existing airframe to keep the costs down. The L188 Electra, which is the root airframe for the P3, was designed to meet the US civil air regulations from the 1950s, very different from what's in place today. There was an increase in the max takeoff weight for the aircraft during production, and whilst it was in service, it transitioned from this notion of what was safe life, or this crack-free period that you could operate the aeroplane, to a period where we thought there could be cracks, and we were having to do periodic inspections to find them. And I have the dubious distinction of being with the NDI technicians in the hangar when we started finding the first fatigue cracks on the fleet. I departed Airbus in November 2019 and instantly took on a much harder role of being Chair of Airworthiness for Gliding Australia, which kept me very busy for 5 years. I stepped down from being the Chair of Airworthiness when A, my 5 years was up, and B, the Pawnee issue came to the fore, and it was largely so that I could focus purely on the Pawnee issue. So a little bit about the Pawnee and its design history. A chap called Fred Week was working at Texas University, and as a design project came up with a purpose-built agricultural aircraft. Most of the aircraft doing ag work at that time were converted military types. He ended up being engaged by Piper to develop the design into what became the prototype Pawnee, and they used as many of the Super Cub and Tri-Pacer components as possible in order to keep the costs down. It was designed to meet US Civil Air Regulations Part 3. This is the 1950s design regs. Important thing to remember, in those design regs, there was no requirement to do any kind of fatigue analysis on the airframe. Fatigue was not understood back in the 1950s. So it was designed to static strength requirements. That was it. No lifetime requirements were considered. It started production in 1957. The maximum takeoff weight was 2,300 pounds. I'm sorry, because it's an American aircraft, I'm going to default to imperial units. I'm sorry for all the metric people. In the 60s, it got upgraded to the Pawnee B, more powerful engines, but importantly, they increased the max takeoff weight to 2,900 pounds. They introduced the Pawnee D with the fuel tanks in the wings in the mid-1970s. Production wound down into the early 80s, mostly because sales had dropped off. Other airframes, larger airframes, air tractors were becoming more economic. And the design got sold to the Latino American Aviation Group in Argentina, also known as Lavia SA. And they started production of their own version in Argentina. I do not know how many that they've built. One of the questions I get asked routinely is, why aren't we seeing inspections on the Super Cup? It's the same wing. So a little bit about forces on the aeroplane. Wings producing lift. The struts on a high-mounted wing are being held in tension. They're pulling the wing down. If you imagine that these struts are trying to pivot around the fuselage, if you try to lift those struts up, they're going to pivot inwards towards the airframe. They are putting compression on the inboard wing between the strut and the root. This is what we call, in engineering terms, a compression critical wing. The compression from the bending and that compression from the strut add up such that the failure mode will be crushing of the spar cap, a bit like a Coke can. Compression critical wings will have low tension stresses predominantly and therefore very good fatigue lives. As a result, the tension stresses are very low. The Pawnees upside down, we've got the wing on the bottom, the opposite happens. If you imagine that the struts are trying to pivot around the fuselage, as they move up, they're going to pull the wing outwards. So that inner wing between the strut and the root is in tension as a result of the strut reaction. Plus, when you include the bending from the local air load, so if you imagine the air loads are going to put a bit of an S-curve in the wing, we're going to get tension on the underside in between the strut and the root, combined with the tension from the strut reaction, and the critical failure mode is going to be tearing of the strut of the spar apart. So these tension critical wings have high tension stresses and will have a much lower fatigue life as a result. Some of the design history, again with the development of the aircraft, the PA-18 wing is very similar to the Pawnee. It's got a max weight of 1,750 pound. They increased the weight for the tripacer by shortening the wingspan, so there's less wing bending on the tripacer. That's how they bumped up the max takeoff weight. With the Pawnee, it's got the same wingspan between the root and the tip as the Cub, it's just got the wider fuselage. They increased the weight to 2,300 pound. I've been fortunate to have a copy of partial bit of the analysis used for the early model Pawnees, and it's a pretty simple wing analysis for stress-wise. With the BCD models and the increase in the max takeoff weight, they took that design to the limit. There is no fat left in that wing, no residual strength whatsoever. It's taken to the absolute limit to get that 2,900 pound. So we're working at very fine lines on the structural envelope of the aircraft to achieve that. Coupled with that, there's potentially what I would consider a bit of a design flaw in the aeroplane. It has a hopper that can contain 150 US gallons that can carry 1,200 pound of water, which is roughly 1,200 pound of superphosphate, depending on how granular the superphosphate is. If it's a pretty fine grain super, you can get more than 1,200 pound in the hopper. That means with full fuel and a mature body shape pilot, you can end up being at well over 3,200 pound, well over your max takeoff weight. And it's my opinion, and there's quite a few anecdotes out there, that the majority of the Pawnee fleet operated by the agricultural community were routinely operating above max takeoff weight. That puts a lot of stress on the airframe. Now, CASA did put out Airworthiness Bulletin 02050 that does allow agricultural operators to operate beyond max takeoff weight, but it's on the proviso that they do a fatigue analysis and work out what the life of the airframe is. I'm not aware of that ever having been done, that fatigue analysis, but I'm pretty sure the operation was happening above max takeoff weight. And even recently, the crash of Sierra Echo Hotel, which is an ag operator in Victoria, the ATSB can't prove it, but they're pretty sure that the aircraft was trying to take off overweight and simply didn't have the performance available for the runway length that it had at the time. So wing stresses are very dependent on the weight of the non-flying parts. If you have less weight in the fuselage, you have lower wing stresses. Some numbers there: operating without weight in the hopper gives 33% less weight in the fuse, thereabouts, and that means 33% less wing stress for the same vertical, G load. So, aeronautical terms, NZ is your G load in the vertical direction, NX is your horizontal acceleration fore aft, and Y is lateral acceleration. So where you see me using NZ, it's all about vertical G. And just a reminder that the agricultural aircraft only operate at those high weights for half the flight. They are transiting out to the drop zone or the application zone, dropping the payload and coming back empty. So that weight saving and that fatigue saving that we get from operating the aircraft very lightweight is not quite as apparent as operating the aircraft at high takeoff weights for 100% of the time. So some recent Pawnee accidents that I can find evidence on. There were 3 accidents mentioned in the service bulletin concerning the holes and the corrosion. I can only find an accident report for one, which is the Columbia accident in 2022. This appears to be the accident that spawned the AD. The aircraft had 13,100 hours on it, and it was caused by a hole with close proximity to the edge of the spar. That's the accident aircraft on the left. The right-hand wing separated as he pulled out of a shallow dive to begin an application on a rice paddy. The aircraft cartwheeled into the ground, hit nose first, ended up inverted against the tree. The pilot was able to extricate himself out of that mess as the wreck caught fire, had minor burns to his ankle as he got himself out of that. The failure was caused by a hole drilled into the corner of the spar cap for a leading edge replacement. The crack expanded from there, severed completely the lower spar cap, had grown up to a point about here before fracturing the spar completely. Of interest to us is this was on the lower cap in between the strut and the root. This is not in one of the current fatigue inspection areas. This is a pretty low stress area of the wing, yet the proximity of that hole to the edge was sufficient to still grow a crack enough that it ended up causing failure. And that crack, that hole was so close to the edge that as soon as they put the screw in, it probably fractured the little little bit of aluminium there to start with, just by putting the screw in and severing that little bit of aluminium that was left. So where are we at with the current inspections worldwide? We're all familiar with the Argentine recommendation, or Argentine AD. We've got a interesting approach to safety by inspection with the aircraft being based on calendar years. We've got the one that we know and love, which is the eddy current every 100 hours or 12 months, whichever comes first. EASA have gone their own way. They still retain the age requirement, which is, again, interesting from a aircraft fatigue point of view. It has the inspections that we're interested in every 4 years or 1,000 hours, providing the aircraft is being operated below 1,000 kilos or 2,200 pound for the uninitiated, and has the external agricultural equipment removed. That means the aircraft has to be placarded to having that 1,000 kilo limit on the instrument panel and changes to the flight manual. The UK has recently been successful in getting an AMOC approved based on the EASA inspections. New Zealand is trying the same stunt at the moment. They are put a AMOC in to try and use the EASA inspections in lieu of the Argentines. They've got a bit of a hold up at the moment where the CAA New Zealand is trying to get hold of the substantiation that EASA used. EASA were not able to provide me with the substantiation that they used for their AD themselves, but they did provide it to the airworthiness people at CASA. CASA have reviewed that and said that it was insufficient to enable approval of an AMOC here in Australia. So it didn't meet their standards. The USA, the FAA put out a proposed AD warning in early December last year. Submissions were closed on the 1st of January this year. I sat down and spent a lot of time with the Soaring Society of America, helping them put together their proposed inspection. They want to go and use visual inspections using an inspection camera, not removing the screws where possible, and they want to do that every 1,000 hours. We're expecting the FAA to make a decision August, September kind of time frame, maybe. It's unknown at this point in time. I am reasonably confident that the Argentines are not going to do anything in the near future until the FAA has made a decision. So to talk very briefly about fatigue life stuff. There was a lot of interest in the 1970s in Australia and other countries in collecting what we call a fatigue spectrum data. Fatigue mechanics as a science had progressed a lot during the 1960s into the 1970s, and was the hot topic in aeronautical circles of the day. A lot of research being done in the area. We were very fortunate. We had a G meter fitted to a Super Cub at Bacchus Marsh, recording data, and a Pawnee at Benalla. We're really fortunate that CASA staff opened a desk drawer, found these sheets of paper lying in the bottom of the desk drawer, no joke, this is real, and they decided to scan it and keep it for posterity. We lost a little bit of data. It was an automatic sheet feeder scanner, and there's a couple of areas where the pages overlapped slightly, so we lost a little bit of data, but not very much. This is the only known fatigue data for glider tying in the world that I know of. It's unique. And this is what it looks like. To understand these charts, you've got your vertical G on the vertical axis. 1G is straight and level. And you've got the number of times per hour you exceed that G level on the horizontal axis. It's a logarithmic chart, unfortunately, it's the way the data is presented. It makes it a little difficult to interpret. But you've got three lines there. One is the agricultural use, which is the dark blue line. Glider towing is orange. And I've put in the general aviation, which is the dotted green line. And that's for single engine private use from American data. So if we were to look at this and say, what's the number of times a glider tug would exceed 2G, it would be 1.5 times per hour. So we're looking at this point of the chart. For general aviation, it's a little less than once per hour. For your agricultural aircraft, 10, 20, 30, 40 times an hour. That's a measure of how aggressive agricultural flying is compared to glider towing. So on average, our positive G exceedances are around 20 times less per hour than agricultural. We are marginally worse than normal single-engined general aviation, and that's mostly because we are doing so many flights per hour. We're doing a lot more circuits per hour. The negative G is pretty much the same all between all operations. When I've been working through the numbers, it's become pretty apparent that what's driving the fatigue life on both agricultural aircraft and glider towing is the ground-air-ground cycle. So wings on the ground, wings in the air. Wings on the ground, wings on the air. It's that bending cycle between those. In Australia, the Australian data shows that agricultural aircraft are doing 9 flights per hour. It's the way that they would deploy to a paddock or a farmer's strip, load up the Pawnee, hop over a couple of fences, start applying, hop back over a couple of fences, land, reload, go again. Whereas in America, they were doing 4.7 flights per hour because they were using a regional airport, transiting out, applying the super, transiting back. In comparison with glider towing, we are averaging 7.8 flights per hour, which is around 6 times more than what the general aviation average was, which is 1.3 flights per hour. Now, this chart on the left-hand side is been modified a little bit from the previous chart, and you see this is the exceedance per flight. So I've worked out how many times per flight we end up going to a particular G level, and you can see there's considerable saving there. However, while working through this, given that agricultural aircraft are all doing all their manoeuvres, all their high G stuff each flight, the length of the flight is rather irrelevant because that's just straight and level transit. It's probably better to actually have the number of inspections based on flights or landings as opposed to per flying hour, which would be your traditional view of looking at fatigue life. And the same goes for glider towing as well. When you're working through fatigue life calculations, it's quite sensitive to small changes in the inputs. Normally, this is backed up by a team of people and not just one individual. You have a lot of material coupon tests to back up the theoretical numbers you're plugging into software, in-flight measurement of loads, and perhaps even a full-scale fatigue test. And I'm pretty sure people have seen either images or videos of airliners or large transport aircraft in the rig having their wings stretched up and down repeatedly, day in, day out. We are probably going to get some material coupon tests, and I'll talk about that in the next slide. When we start talking about fatigue life calculations, you've got 2 phases, this initiation phase and a growth phase. With initiation phase, we're talking about the formation of a proto-crack at the microscopic level in the metal. It has a lot of scatter in the calculation just due to the differences in the metal and the changes at the micro level. We have a bit of a problem in that we are using these thread-forming screws in the metal. It's not a clean round hole. there is very, very little data available on the effect of what these thread-forming screws does on the crack initiation. Because thread-forming screws are not used in fatigue-critical areas on aircraft design. This is possibly the world's only aircraft where this happens. So at the moment, when I present the numbers, just bear in mind that I've had to account for a few known unknowns here. I've used much higher stresses at the screw holes to account for the fact that I don't know quite what's going on with the thread forming screws at the moment. As of beginning of March, I now have 2 master's students at Adelaide University Engineering starting coupon testing, where we are going to be getting some samples of 6061 T6 aluminium sheet, not extrusion, sheet metal. And we're going to get some little samples in a machine that's going to stretch the metal repeatedly for hours on end to start developing cracks at holes. We're going to do 3 batches, a smooth round hole, which is going to be our control batch, some samples with screws fitted, and then samples with screws fitted then removed. And then we can start trying to sort out what the impact of the screws are on crack initiation and development. And the results will come out later this year. The imagery on the left is from a Japanese technical paper that was published in 2024 talking about the stresses imparted on the metal as the screws are inserted into it. Some of the interesting things is what they theorise is as the screw is being inserted is shearing the metal around with it as it's being deforming the thread. So it's being carried along with the thread and then moving down the thread as it goes along. So you're getting these wave patterns as it's being deformed. The impact on fatigue is you are cold working the material. You're changing the material properties as you're putting this screw in. So you may well find that despite having a really jagged screw edge, which is typically bad for fatigue, the cold working of the material might toughen the material so that it cancels out. Toughening up the material makes it more fatigue resistant in the initiation phase, and it might simply help cancel out the impact of having that jagged screw edge in the metal. The other downside is that around the area of metal that's been deformed, you'll have a donut of metal that's still being stretched, but not enough to deform it. That area of residual tension will result in, if the crack goes into there, it will accelerate the crack growth because you've got this extra little bit of tension from around that field. We will hopefully get some results on that later this year. So once the crack grows beyond the area affected by the thread forming screw, it's relatively predictable mathematically, give or take a bit. Again, I've used a much higher stress in the early stage of the crack growth, mostly to do with the unknowns with the thread, but that stress is pretty good for the late stage. If the crack grows into the spar cap, I'm using the spar cap stresses, so the crack growth rate in that late stage is pretty good. So these are the results at the moment based on using eddy current as your inspection technique. You can expect to start finding cracks in an agricultural aircraft that's been operated regularly beyond the max takeoff weight after about 3,300 hours of use. If the ag pilots behave themselves and stay below max takeoff weight, 7,800 hours. That's not a bad number. When I went into this, I was thinking, based on other work and other aircraft types, 8,000 hours on an ag aircraft is pretty reasonable as an answer. For a glider tow plane with spars that have only done glider towing is something astronomical. We are so benign, it's not funny. That 1 million hours is not a joke. And even if you don't trust my numbers and start dividing that number by 5 as an extra safety factor, you're still in the order of 300,000 hours. If you're doing 150 hours a year, what's 2,000 years worth of flying? Inspection intervals, agricultural use over max takeoff weight, 150 hours. Normal agricultural operation every 200 hours. Glider tow plane, after it's exceeded these kinds of lifes up here, every 2,100 hours, based on the numbers at the moment, using eddy current inspection. And here's where I get lynched. The areas that the AD are focusing on are based on where they've had crack detection and crack failures in service. These have all come out of holes which have been what you would consider abnormal to the design. Holes that have been too close to the edges, holes that have been drilled too close together. The AD does not allow for these holes to allowed to go flying anymore, so they should be removed from the gene pool. Which means what other holes are nearby that are similar to the leading edge screws that are also in high stress areas? And unfortunately that means it's the rib holes. The screws that are in the nearby ribs are identical to the screws that we're using on the leading edges. Now these have been drilled with a jig at production so that they fit up to the rib. So they're all very centre to the flange on the spars. There's no holes that are close to the edge of the rib holes. They're not going to be removed as frequently, so there's less damage to the hole by the remove refit cycle. But the major ribs have 4 screws, 2 on the forward side, 2 on the rear side, and the intermediate ribs are on the forward side, and there's only 2 of those. But in all honesty, in my opinion, we'll need to start inspecting the screws on the forward face of the spar as well, because they are still a risk area that is not being addressed by the current AD. So, despite having done all those numbers, I've been asked to reconsider the work that I've done so far and try and find a way that we can do this via visual inspection techniques. And this is synergistic with what the Soaring Society of America proposed to the FAA by using an inspection camera that can get into the gap between the flange and the spar web and check for cracks visually without removing the screws where possible. Visual detection is the least trusted method of inspection for cracks. Everybody trusts eddy current, nobody trusts visual inspections. This is going to be a pretty hard sell to CASA. We're going to have to come up with some fairly convincing arguments as to why they should allow us to go down this road. When we talk about inspection methods, we talk about how likely it is that that inspection method is going to find a defect that is there. So when we're talking about eddy current, which is an orange line, there's been a lot of study done on this technique, and it says that at 1¼ millimetre, or 50 thou in the old language, you've got a 90% chance of finding a crack of that length. So if you're using eddy current, you will set yourself up so you'll have 3 inspections between when the crack becomes detectable at that 1¼ millimetre length through to what your maximum crack length criteria is. And you'll have 3 inspections set up. The first inspection gives you a 90% chance of finding the crack. The second inspection gives you a 90% chance of finding the 10% you missed, which gives you 99% in total. The third inspection gives you a 90% chance of finding the 1% that the first 2 missed, so you're now at 99.9% chance of finding the crack. We will need to try and do the same sort of thing with visual inspection. The dotted line here on the curve is a curve that I've made up based on some Boeing data, and it suggests that a 7.5, nearly 8mm crack would be 90% detectable using visual inspection. That's a little misleading, I think. I'll talk about that in a future slide. But visual inspection is going to be very dependent on the gear that we are using. It's likely that we're going to need a specific bit of equipment with a minimum camera resolution. The proposal is already put before the board that we should be considering purchasing some inspection cameras specific for this task, and that can be hired out to clubs. The other way of just looking at that last dot point there is if you aren't happy with trying to find a long crack a few times, you can get that 99.9% chance of detection sort of standard by trying to find a shorter crack more frequently. So you have a decision point. Is it worth looking more frequently with a worse chance of detection, or do you look less frequently with a better chance of detection? It's a bit of a cycle that we need to work through to try and sort this out. These are some examples. The inspection camera is very dependent on the quality of the optics. We are trying to get a 3mm diameter probe in between that area. 3mm diameter camera is pretty limited in terms of what you can get in terms of resolution and the quality of the optics. These are photos from the Science Society of America with the demonstration that they were using for the FAA. These are all inside the flange. Note here that all this material has been deformed out of the hole by the screw thread going into the hole. Important factor to note that this little defect here, this with the splurge has come out, that's probably bad enough to give you a false alert with the eddy current, and you can't see that from the outside. So you can have an eddy current giving you a crack alert, which is not really a crack. Some of the things that we need to be thinking about. On the ground, the weight of the wing could be holding the cracks closed. Whether or not you can see it on a digital camera depends on whether the crack is actually wide enough to be picked up as a pixel. So not so much the length, but it's also whether the crack is open or closed and wide enough to be detected. So the counter to this is you may need to apply a little bit of force to the front spar to open the crack to make it more visible. The other thought is leaving the screws in the holes has a number of benefits. It prevents damage to the holes. Because you're getting that ring of tension around the outside of that screw, it's going to be opening the crack. Leaving the screw in situ may help make the crack more detectable visually. The downside is the tail of the screw may obstruct your visibility. So if you're looking in this instance for a crack coming out towards the flange here, the screw's in the way of a short little crack there. You can't see it. You're going to have to be moving the probe around to try and make sure you've got a good view either side of the screw. We've had one crack detection on an Australian aircraft. That's at Narromine. I've now got, as of last week, a 3mm inspection camera here. And today is the first time I've had it in the same room as some Pawnees spar. So if people are interested, we can come and have a little play at lunchtime with the camera and the Pawnees spar and just see what we can see. But I need to get myself over to Narromine. I've got a diesel car. Hopefully there was fuel enough on the way there and back again. Or I'm going to be stuck somewhere in the countryside. Can we see cracks? The camera we've got at the moment is a reasonable resolution camera, but the screen's a little limited. There's a few things we can do there. My testing shows a minimum focus distance of 8mm, which is pretty good. My testing so far shows that we can see down to at least 60 microns, which is the diameter of one of my hairs. That's in good conditions. I've been on to the manufacturer. They say JPEG images were a bit grainy because they had a lot of JPEG compression. They've now given me a firmware update where that JPEG compression's been removed. And I have a lump of aluminium off a P3 at home which has some stress corrosion cracking. And there's an example of it there. These little hairlines is the stress corrosion cracking in an angle of 70-75. Of note is there's a little line there which is a stress corrosion cracking. That's all of 2 millimetres long. So it's not so much the length, it's really the width of whether you can detect it with the camera. I have here a sample from an Arcus, I think it was. I know this is cracked. I know where the cracks are. The cracks are 2.5 to 3 millimetres long. Because these cracks are closed up and very tight, they're not under strain at the moment, I am having a lot of trouble seeing them with the camera. And this is even when I know where they are. So having the cracks open is going to be the critical bit, one of the critical links in this case. So the proposal at the moment will be to install some access panels in the lower surface of the leading edge so you can get to the access to the ribs on the front of the spar. We'll be inspecting both the rear and the front screw holes. This will be in 3 areas on the wing root on the lower surface, in the hard walk area, the existing inspection area on the upper surface between the root and the strut connection, and under the strut connection on the lower spar. Not to remove any screws except on the aft face of the lower spar under the strut where that reinforcing strap is located. It's unlikely we're going to be able to get the camera inside there. The inspection interval may be between 500 hours and 1,000 hours. I haven't done the numbers yet because I've got to work out what sort of crack length we're going to be able to see. And the regions will need to have suitable inspection cameras available. So the one I've got there is the cheap version with the shorter lead on it. The long version's got $1,000. So the regions will probably have 2 each, or in that order of magnitude. And if you're inspecting every 3 to 5 years, it should be plenty for the clubs to be able to use and abuse. Other stuff in the meantime, just because I'm a sucker for and a bit of a masochist, CASA have an AD out for inspection of the wing root fittings. We've got 6 aircraft that still have the unmodified wing root fittings on the fuselage. 5 of them are single seat, one's the 2-seat conversion. The stress analysis tools, I created a spreadsheet that does calculates in-flight loads on the spars for the Pawnee under arbitrary flight conditions, and another version for landing and another version for taxi. That gave me some very good tools in order to analyse what's going on with the wing root connections. I've got a report in with a Part 21 engineer at the moment which recommends increasing the interval to 6,500 hours instead of 500 hours on the single seat, 5,400 hours on the 2-seat. Now that number for the 2-seat was based on the particular weight and balance of that aircraft. It's not applicable to all the 2-seat Pawnees. So that's with the Part 21 at the moment. Hopefully we'll get that through to CASA in the next few weeks. Any questions?
Is the current work with the camera is to assist getting a change to the CASA's AD requirement of these testing every 100 hours and so on?
It's not a CASA AD, it's the ANAC AD. So yes, the idea is to put a proposal into CASA Airworthiness to say that we want to inspect every, say, 500 hours or more using the inspection camera in these locations in lieu of the ANAC AD.
Who's going to be authorised to carry out these inspections?
That's a really good question.
Because that's going to be where you're really going to be wanting to have people who are independent of the operation rather than actually have a vested interest.
That's going to be a question whether it's going to be a LAMI being that it's not a Gliding Australia airworthiness thing, it's a LAMI thing.
Does it need to go that way up? Does it need to be a lane? Could not an Amy do it?
Possibly an AMI. That's a really good question. It does not need to be an NDI tech, and one of the problems that many clubs have found is just getting an NDI tech to do the eddy current has been a major problem. So yes, a very good question, well asked. Anybody else? Good.
We'll hold them.
Oh,
Hold them.
catch me at lunchtime, perhaps.
Yeah. Catch them later.
Sorry, GAus be providing the cameras to each region?
There's a proposal to the board. This is part of the reason for this discussion. We want to show you what's being considered. We need to test whether or not CAS is going to be open to these sorts of alternative inspection regimes. Okay, we'll press on. Thank you very much, Anthony. And I thank you for your professionalism and dedication in pursuing this. It's a long road to hoe.